So Jonathan, can you explain in simple terms what is a quantum computer and how is it different to a classical one?
Okay, so a normal computer works by processing data as zeros or ones in what's known as bits. On a quantum computer, we replace those bits with a quantum bit, which is a two-level quantum system where we have essentially the representation of 0 and 1, but now quantum mechanics gives us some new properties. One of these is superposition, and now instead of this qubit being in state 0 or state 1, during the computation it can have this new property of superposition where it can be 0 and 1 at the same time. Where this becomes really interesting is as you increase the number of qubits, every time you add one more qubit, you double the number of different states that you can represent. And so this becomes exponentially growing in the size of the storage. Whereas for a classical computer, if you want to double the power, you have to physically have a processor twice as large.
So what are Rydberg atoms and how can they be used for quantum computing?
So Rydberg atoms are atoms in really highly excited states. And so to think of this, you normally have a neutral atom. It's a positive nucleus surrounded by a ball of negative charge, and the electrons start quite close by. If you excite these to Rydberg states, essentially you're taking one of the outer electrons and moving it to a very highly excited state. It now moves very far away from the nucleus, and it acts like a really big antenna. This makes Rydberg atoms really good for sensing electric fields. So people have used these for microwave, terahertz, and RF detection and communications. But in the context of quantum computing, we use this in order to engineer strong interactions between atoms. If we take atoms on a length scale of 5 to 10 microns, we put them both in the Rydberg state, these big antennas essentially act with strong interactions, and we can use that now to couple the atoms together to perform our gate operations during our quantum algorithms.
So what are the advantages of these Rydberg atoms over other technologies that are used for quantum computing?
So neutral atom arrays are based on taking lots of individually trapped atoms and then coupling them to these Rydberg states to make them talk to each other. One of the major advantages of this is these atoms start off neutral. They have no charge. And so if you go from having one to many of these, they don't talk to each other initially. And so this overcomes one of the major challenges of ion trap systems where ions are really highly charged. Every time you add one ion, all the others know about it. This means we can combine this ability to scale with techniques of laser cooling and trapping to go from sort of tens of qubits to even thousands of qubits with no loss in performance. Compared to superconducting circuits, the other major advantage is these atoms have properties defined by nature. And so every atom in the system is identical, and this means as we scale the systems up, we're not fighting the problem that if we're using kind of like handmade or fabricated qubits, each one of those will have a local difference. Here the atoms are all completely the same as we make the system bigger.
So what problems will quantum computing solve for us, and how might that look on a day-to-day, on an everyday basis?
So quantum computing has the potential to speed up a wide range of different types of problems. So these are both problems that relate to quantum systems. So this would be thinking about, for example, understanding how molecules work, quantum chemistry, as well as understanding how material physics works. In the near term, people are looking at other areas where, for example, classical problems that are combinatorically challenging. So this would be factorization, route planning, deciding on, for example, how you pass information around a network. These are all problems which we can find reasonably good guesses to, but at any scale classically, it's beyond the scope of what can be calculated. On a quantum computer, you can find algorithms that can really speed up the efficiency with which you can find these solutions, and now not only find a good solution, but actually find an optimal one. And here this might have implications in, for example, traffic management or distribution of energy around the grid.
So quantum computing at scale is a long-term investment. On a personal level, how would it feel to make a breakthrough or a substantial contribution to this?
So since I started my PhD, I've been really excited by the field of quantum computing. And as part of my research group here, I've built up one of the UK's largest activities in neutral atom quantum computing, working quite closely with industry, where together with our partner M Squared Lasers, we've been able to build the UK's first large-scale neutral atom systems and then push that through to industry. So, I mean, the thing that gets me out of bed in the morning is actually coming in the lab and seeing new science happen. And so being able then to turn that into something useful and have it not just be something that we enjoy doing here, but really see it pushed through to, for example, looking at applications. It's interesting seeing how do we use that? How do we solve the technical challenges required to make the hardware work? And then how do we turn that and actually apply it to real or near-term problems? And that's been a really interesting adventure, and it's what keeps the job exciting.
What role does creativity play in scientific research?
I think creativity is hugely important. If we think particularly in the context of quantum mechanics, most of the early theories were developed partly by measurements, but also by these thought experiments. So Einstein was thinking with his Gedanken or thought experiments. he was the one that started thinking, what does it mean to have entanglement? What does it mean to have two particles that can be entangled and, for example, be separated to the ends of the universe and have a measurement on one instantly affect one on the other? And so one of the great things is this creativity has driven people to build some of these, what would have previously been kind of absurd thought experiments, and actually now they're realities in the labs.